Hello, everybody. Welcome to today's current seminar. Today we have one speaker, one talk. Our speaker is Ramansh Sharma. He will be giving a talk on ensemble and mixture of experts, DeepONets for operator learning. Ramansh is a second-year PhD student at the Collard School of Computing, University of Utah, working with Professor Varun Shankar. His research focus is on developing interpretable and trustworthy operator learning frameworks for real-world scientific applications. With that short introduction, the floor is yours, and you can start your presentation.
Awesome. Thank you, Nas, for that great intro. I'll start. Hello, everyone. I'll be presenting this paper today. So we actually recently published it at TMLR, Transactions on Machine Learning Research this year. And let me just put Zoom on the side. Perfect. If at any point my audio disconnects or something, please let me know. Okay, so let's begin. So this is a rough outline of the talk. I'll first give a quick overview on operator learning, and then get into what one of the most common operator learning frameworks, architectures, the DeepONet is, and what it looks like, and then go into what we contribute in this work, what we call the Ensemble DeepONet, and then discuss a variety of results from the paper, and then share some insights from those results. So first, a quick background on operator learning. So given the normal audience of the Crunch seminar, this is probably repetitive, but just for the sake of consistency in this talk, I'll quickly talk about this. So in operator learning, the goal is to learn a map between two function spaces. Instead of in normal machine learning, one would try to learn it between two vector spaces. So given two separable function spaces, U and V, and many different functions from those spaces as the data set that one is given, the approximation G hat with some parameterized by some trainable or fixed parameters theta becomes the operator map that we try to learn. And the way we try to learn it is by minimizing some sort of error between the approximation and the true operator map. Examples of operator learning can be to learn or approximate or fit the operators that look like the first derivative operator, or the Laplacian, which is the sum of second partial derivatives, or the integral transform, or anything that transforms a given function u, for example, into anything separate from u. So addition could be one simple operator that could be learned. And the goal is to learn that mapping, the action of that operator, so that in the real world, when we give the learned operator a previously new unseen function, it can give us the action of that operator on that new unseen function. This is especially useful when it comes to approximating solution operators of partial differential equations. So once a neural operator has learned and approximated that operator, one does not need to run numerical solvers on new functions anymore. You can just do inference with the learned operator. Okay, so let's go into DeepONets. So DeepONets, first, published with the 2021 paper by many people from Brown, consists of two neural networks, the branch and trunk. The branch is responsible for learning a nonlinear representation of the input functions, and the trunk neural network is it represents a basis for the output functions. And the way one would then approximate the operator is by taking the inner product between the branch and the trunk neural networks, which now becomes this nonlinear combination between input functions and basis functions for the output functions. And then the G hat U of Y approximates a given output function of any operator applied on you at a given location Y. And then, given a large data set of input and output functions, this error is minimized between all pairs in the training data set. And then one can apply this at inference on new unseen functions. So that's, I think, a sufficient background on DeepONets for this talk. So one of the things that we wanted to do in this work was use DeepONets to learn the solution operators of partial differential equations that have interesting local features. And naturally, our attention turned towards something from the scientific computing literature, which is called partition of unity. So we tried to incorporate that into DeepONets. And the way we did it is by creating what we call a partition of unity mixture of experts trunk. Now, let's discuss first, a little bit of background on what the core idea is. So it is motivated by the partition of unity literature from decades of mostly scientific computing and PD literature. So the way it works is that given a domain, we partition it into a set of overlapping patches. Now, these patches do not necessarily have to be spherical patches, but for simplicity in this work, we stuck to spherical patches. So we partition the domain into these overlapping patches. And then the key idea is to have some sort of an approximant on each of those local patches that are then blended together. In our idea in this work, the idea is to have a trunk neural network on each of those local patches and then blend them together into an ensemble trunk, which I will discuss a little bit later. So this partition of unity mixture experts trunk can then be written as a weighted sum of each of the local trunk neural networks on each of the on the individual patches. And the weight functions need to have some special properties as well. So in this work, we picked C2 differentiable Wendland kernels to be the weight functions, which look something like this. These are radial basis functions. And the reason we picked this specific kernel is because of its compact support. So imagine this kernel, the Wendland kernel, placed on each of the 6 individual patches, for example, from 2 slides ago, that weight the neural networks that are sitting on those individual patches. And then this weighted sum turns into the partition of unity mixture of experts trunk. And the weight functions, as from the partition of unity literature, need to have the partition of unity condition imposed on them, which means that for any location in a given domain, all the weight functions that contribute for that point must globally sum to 1. So this ensures that this ensures certain approximation properties. So this is all so this is a necessary constraint when using this trunk neural network. So this is one of the interesting trunk neural networks that we created for this work. Now, each patch's trunk neural network can now be viewed as a spatially local expert, which means that the whole global partition of unity mixture, the POU MOE trunk, has certain advantages that a normal global trunk neural network does not have. First, because of the compact support of the Wendland functions and the way it weights each of those trunk neural networks, each of the, for example, 6 individual trunk neural networks only contributes to the points in their domain. that means that the overall weighted POU-MOU trunk is extremely sparse in its experts. Because if you have 6 different neural networks, trunk neural networks on each of the patches, one does not have 6 times the number of points as the basis functions. So it is extremely sparse. And since the overlapping patches cover the domain entirely, the weighted sum is still a global set of basis functions. So so the partition of unity mixture expert trunk is still it constitutes a global set of functions, and it is a universal approximator. So if I have time at the end, I can go through the proof of that if people are interested. But yeah, so it is also a universal approximator, just like the original trunk neural network in DeepONets is. Okay. Uh, Next, so one of the other important contributions that we made in this paper is modifying the POD trunk a little bit. So the POD trunk, I think first introduced in the fair comparison paper, 2022. It uses the proper orthogonal decomposition of the output functions as a set of global basis functions. So in this work, because of what I'm about to describe in the ensemble architecture, we also included the mean function from the POD decomposition that the original POD trunk did not use. So throughout the rest of the talk, the modified POD means it includes the mean function and the set of basis functions. And the lowercase p here that I'm using to denote is just for example, the number of basis functions that one would have. And that would have an inner product with the branch neural network, again, that has lowercase p coefficient values as a function of the input functions. Okay, now to the ensemble DeepONet. So the goal that we had, the motivation that we had when creating the ensemble DeepONet was, okay, the normal vanilla DeepONet has a trunk neural network that constitutes a global set of basis functions. And because it is the trunk neural network sees all of the spatial points at once and learns a nonlinear set of basis functions. We wanted to combine local basis functions into the mix. So how do we do that? We took a simple approach to creating such an ensemble. The key idea is that if one has a certain number of trunk networks, let's say 3 of them, the way to create an ensemble is to just simply horizontally stack them to create just a larger set of basis functions. The branch neural network, accordingly, just needs to create more coefficients as a function of the input functions. And in terms of implementation, this is fairly straightforward. Most neural network and machine learning frameworks have vectorized operations which allow to stack different trunk neural networks, and the total number of these basis functions is just a hyperparameter. So P1 plus P2 plus P3 is trivially set to, even in the branch neural network, to create as many more coefficients. So that is the key idea behind the ensemble DeepONet. And this is what the architecture, for example, would look like for a combination between the partition of unity trunk that we talked about and the POD trunk. So if we have 2 sets of these basis functions, we have a total of P1 plus P2 basis functions that are weighted by the branch neural network. Okay, so that covers 2 of the novel trunk architectures that we proposed in this work, and a way to combine them at the same time to use in an ensemble architecture. Now, the next question that we wanted to ask ourselves was, what makes a good ensemble trunk? Well, naturally, it is to combine trunks that have different properties. And we tried to investigate which set of properties in an ensemble architecture result in not just the best performance arbitrarily, but um, that outperforms certain other networks in which situations. Like where do those properties shine? So the different properties that we decided to investigate were, for example, the vanilla trunk architecture, the purity, or the modified purity architecture, and our partition of unity architecture. So for example, the vanilla purity, the first one, architecture, asks whether adding purity modes to just a normal global set of trainable basis functions helps. Helps it be more expressive and learn better. Or does adding spatial locality to the vanilla trunk make it more expressive? We also decided to get rid of the vanilla neural network altogether and just see if having the POD as the global modes and the partition of unity trunk as the set of local modes is enough to be expressive for certain problems. And does on top of that, adding more trainable parameters in the way of adding another vanilla neural network as a trunk helps further. Finally, we also have this baseline architecture that we called P plus one vanilla. So here, P is the total number of patches that we would decompose a domain into. So just to be fair, while comparing these architectures against each other, because the partition of unity trunk has a larger number of neural networks, because it um, has a separate neural network on each of the individual patches, we created a simple P plus one vanilla architecture that has P plus one vanilla trunks stacked horizontally to see if simple overparameterization is competitive and one does not need all these fancy tricks to be more expressive or, as I'm about to show, resolve certain spatial features better. And spoiler alert, it turns out that the best architecture among all these is the POD-POU architecture across a variety of problems. So given that, I'm going to move on to some results now. So first, the first problem that I want to get into is a 2D reaction diffusion problem. So in this problem, we are trying to model the concentration of some sort of material that is in a square domain, 0 to square domain for some amount of time. So there's reaction and diffusion terms in the main partial differential equation. And there's two coefficients here, k on and k off, that are chosen such that we introduce a sharp spatial discontinuity in the solution. So what happens is, as the material starts reacting and diffusing all throughout the domain, we strictly cut off any reaction terms that are happening at like a vertical line, as I'll show in the next slide. So the goal then is to learn a solution operator from the initial condition, that is samples from, I think, a uniform distribution, to the final solution at time 0.5, some final time. So here are some results on this problem. So we have examples of the input and output functions on those figures, and the partition of unity patch placement that we did. And throughout the other results too, I'm going to be showing the spatial mean squared errors of the vanilla DeepONet and two of the best ensemble architectures. So right off the bat, we can see in the output function figure that the sharp discontinuity is quite significant. So that is certainly an interesting feature and realistic in many problems. And our results showed us that the best model in this case was the POD-POU ensemble. It completely, really well resolved the spatial discontinuity there. And the second best model was the overparameterized one. But just to show that this isn't just because both of these models have more trainable parameters than the vanilla DeepONet, and that's the reason they did better. We're going to discuss spatial locality. So this is one of the things that, as we went through the review process, we needed to find better ways to articulate and display more. So um, what we observe, so what I'm showing here are two basis functions that come from the trunk neural networks. So on the left is the most important basis function corresponding to the largest branch coefficient of the vanilla DeepONet. And on the right, we have the most important partition of unity basis function coming from the POD-POU ensemble trunk. And we can clearly see that the patch placement strategy that we employed in this problem corresponds to the basis functions that it learned. So I'm only showing one of the basis functions here, but all the others, so we used, I think, 100 basis functions here. So all the other partition of unity basis functions have this structure in them. Their spatial variation corresponds to the patch placement strategy. And we believe that this is, and they're on a similar scale, both the vanilla and the partition and the POU basis. And we believe this spatial variation, especially when combined with the POD global modes, is what is responsible for consistently better performance of this architecture against all others, as I'll show for the other problems. Now, this is admittedly not strong evidence that this this spatial variation is literally what results in better performance. But other than this, there are no other um, um, differences between the vanilla DeepONet and the POD-POU DeepONet, because the P+1 vanilla DeepONet, its basis functions obviously do not have this nice spatially varying structure. Okay. Next, we decided to take it up a notch and create a much harder problem to solve. So first, we turned the reaction diffusion problem from 2D to 3D. And in addition to still having the same spatial discontinuity at a vertical, so here it will be a plane, we also decided to introduce this coefficient function k of y that is extremely nonlinear. And that results in the diffusion term being extremely nonlinear in this equation. So we have a sharp spatial discontinuity that we artificially introduce, and sharp and steep gradients that emerge from the diffusion term. The operator that we try to learn is still the same from the initial condition to the solution at some final time. And these are what the results look like. So here we needed to, naturally, since we moved to high dimensions, we needed to pick 8 patches to cover the domain entirely. And interestingly, most of the architectures of the list of models that we decided to investigate with had around 5% relative L2 error on the test data set. And only these 3 models had errors that were this low. And even compared to them, comparing these 3, the POD-POU architecture outperforms everything else significantly. So it can resolve spatial disk. So that is one of the key insights that I'm going to be talking about later, that it's whenever the problem had these sharp gradients, either artificially introduced or coming from something like a diffusion term, that's where the partition of unity trunk shines the most. Okay, so the next 2 problems that I'm talking about come from the fair comparison between DeepONets and FNO's paper. So one of them is the 2D lid-driven cavity flow, where we have the Navier-Stokes equations, and we have a 2D domain, and the upper lid starts moving spontaneously with some velocity. And the operator that we try to learn is from that velocity function, the boundary function, to the final solution. Now we're working with the steady state solution, so it's just what the solution ends up being as the impulse boundary function dissipates with advection and actually just diffusion in the equation. Okay, so for this problem, we observed something similar. Not a surprise anymore that the POD-POU function architecture outperforms all the other models significantly, especially just the normal vanilla DeepONet model. And you'll observe that, again, for many of these problems, actually, up until now, the P+1 vanilla DeepONet has not been the best performing one. So it is not simple overparameterization does not help in most of these problems compared to something more clever. And just to show as an example here, we picked patches that were not of uniform sizes. So that is an advantage of this technique that one can place patches of different sizes in features that are more interesting. And while we had the same hyperparameters for all the individual trunk networks on these spatial patches, they don't have to be. Like one can use different activation functions or different number of different neural network architectures or other hyperparameters for each of the individual trunk neural networks.
Sorry, I have a question here just for clarification. So the
Mhm.
numbers that you're showing here are the percentage, right?
Yes,
The
they're
percentage of the relative okay.
yes, yeah.
Okay, thank you.
Sorry, I should have mentioned that. Yeah, the relative L2 errors are shown as percentages on the test data set here. Okay. Finally, the last problem that we checked in this paper is the 2D Darcy flow problem. Again, coming from the fair comparison paper. Um, so here the domain is a triangular domain, and the solution operator that we try to learn is from the boundary condition. So it is a one-dimensional boundary condition to the solution in the entire domain. So these are the results on this problem. So interestingly, in this problem, since there were no, at least relative to the other problems, there were no interesting features for spatial partitioning to resolve. The PUD-PUU architecture is not the best architecture here, but it is still certainly better than the vanilla DeepONet, probably because um, um, having localized basis functions still helps. But on top of that here, having more trainable parameters helped more. Like it ended up having a better accuracy. Again, the P+1 vanilla is not the best. In fact, here I believe it was less accurate than the vanilla DeepONet. And that was a strong insight that we had in the paper, that overparameterization not only most of the time does not help, not only most of the time is not the best, but also sometimes it hurts in certain problems. So this was the 2D Darcy flow example. And now to discuss the insights. So at the end, the big question was, what makes a good ensemble trunk? And as I've been pointing towards it, it is a mix of global and local basis functions. So here, the yes/no refers to whether these models outperform the vanilla DeepONet, and the bolded versions are the best performing models. And we can see that all the best performing models have the PUD global modes and the partition of unity mixture of experts local modes. In the case of Darcy flow, having additional trainable parameters in the form of another vanilla trunk help more. But for problems with interesting features or spatial high spatial gradients, um, our model outperforms other models by at least 2 to 4 times in terms of the relative L2 error. So that was the most important insight from this paper. So to conclude, yeah, I think the presentation ended up being a bit shorter, but yeah, to conclude, the ensemble DeepONet that we introduce here, first of all, is a way of enriching the basis functions in a DeepONet, which is not that easily doable in other architectures, because there's no clear viewpoint of what a basis function is in many other neural operator architectures, for example, like FNOs. But with DeepONets, the trunk neural network is clearly a set of basis functions. The POD-POU ensemble in this work consistently outperforms the other models. And as I just mentioned, it is a judicial combination of local and global basis functions that performs, that is vital for many interesting problems. Yeah. And in the future, one of the things that we are working on right now in another project is expanding the way we partition the spatial domain to not have just static domains and spherical domains all throughout training, but allow it to deform or change shape as it goes. Because in many problems, spherical patches are um, not the most useful ones. For example, in the Darcy flow example, since we have a triangular domain, it would make more sense for like an entire domain to cover each of the three boundaries. So an ellipsoidal domain shape would be better. And that is easily doable right now in the framework. But in order to make it deformable, we have to do something interesting to have the patch shape and size change dynamically throughout training. Um, we're thinking about expanding the ensemble learning strategy to other neural operators like FNOs or graph neural operators. For FNOs, we do have one of the ways that we can do it. So we have an idea on how to do it with FNOs, but we would have to think about how to do it with other neural operators. But it's anything that can be viewed as a set of basis functions um, can be decomposed into local and global modes spatially. And with that, yes, thank you so much.
Thank you so much, Ramesh. I think that Nazanin had a problem with her network, so she asked me to take over. Do we have any questions from the audience?
Yes, I have one question.
Yes.
Hi, this is Ahmed from Brown. So I saw the examples, and I'm wondering if you can test your framework on an inviscid high-speed flow problem with shock waves, since it works with discontinuities, and that would be like a suggestion, and then just yeah, to compare with other existing networks, because we have a paper, we used two-step training DeepONet. I don't know if you've heard of that. And in that, we learned a very discontinuous problems, like with shock discontinuities of like 1 billion pressure
I see.
difference. So, so it
I
would
think
be interesting to compare.
No, yeah, absolutely. I think yeah, Shockwaves is certainly like a well-suited application for for this work. Um, so yeah, like actually, in fact, my next slide, like as a like appendix, just to show, for example, the kind of coefficient functions, the variable coefficient diffusion that we used for the 3D problem, it was very had very steep gradients. It was highly nonlinear. So I think yeah, for shockwaves, I haven't worked with them so far, but yeah, absolutely. Like
Yeah,
certainly,
shockwaves are a bit different. Like they're like discontinuous. So basically, it's
yeah,
different than having a big gradient in a smooth function.
yes, you're right.
So yeah, so yeah, it would be interesting to just, just compare. Yeah.
I think so. Yeah. Thank you.
Thank you.
Do we have any other questions for the speaker? I don't see any raised hand. So thank you so much for your great talk. And thank you everybody for joining us today. It's time to close the session. Have a
Thank you,
great
everyone.
weekend ahead.